All right, so it's being recorded. All right, so our focus now is shifting to arrays and structures. Okay, so before we get started, I just want to point out that I have reworked the notes regarding arrays and structures. So this is actually reworked. It will link you to the GitHub version. So it's already rewritten, everything in here is correct, but it is awfully dry. So what I want to do instead is to use GDB to illustrate some of the concepts that is already illustrated here. Okay, so that's what we're going to do. So what I will do is to go to one of my text interface here and show you the actual code that is useful for this illustration. All right, so before we get started, are there any questions about structures and arrays from CISP 360 that you might want me to address before we start to talk about arrays and structures, but not in the context of assembly language programming? So I'm strictly talking about just 360, CISP 360. Are there any specific concept that you want me to address before we get started with this topic? First of all, did you guys talk about structures? Did you guys talk about arrays? Okay, very good. So what we'll do is we are just going to look at some programs just for structures. So I'll go ahead and write a program. I'll just call it struct.c, and I usually want to include standard integer.h just so that I have full control over the width of integers. Okay. And here we define the structure. The name of the structure is X. Okay, so this is not what it's creating. This is really just the structure itself. And we'll just say that int8 underscore t, it has 5 members. Okay, so I'm going to use M1, M2, M3, M4, and then M5. Those are members of this particular structure. So are there any questions about line 3 to 5 of this code, which is basically declaring a structure that has 5 members, M1 to M5. Each one is only 1 byte wide. Are we good here? All right. Okay. So what we'll do next is we're going to actually write some code. Okay, here's main. And main has one single variable of the type struct X. And we'll call that, okay, I'll just call it ABC. Okay, ABC is the name of the local variable of main. It is of the type struct X. And we have a return 0 here. Just to make sure the compiler does not optimize everything out, I'm just going to say, M1 member, the member M1 of ABC is going to get a value of 0. That's all. Okay, so this program doesn't do anything really useful. But if I look at this program through GDB, well, we can actually find a few interesting stuff. Is that okay? All right. So we'll get out of here. GCC-G, which allows debug symbols to be inside the executable. -O means this is the output of the compiler. So it will give me an executable of struct, and then the source code is struct.c. So I just like to do everything on the command line. GDB struct, okay, we are now inside the debugger. And we'll put a breakpoint on line 11 because I don't even need to run the only statement of this program to illustrate what I need to illustrate about structures. So I run the program. And the first thing I want to do is to say, okay, tell me where is ABC as a variable. Okay. Can everybody see, including the bottom of the screen? Because people in the back may have a little bit of a difficulty. Let me kind of pull this up a little bit so that people in the back can, also see this. Is the font size okay? Okay. All right. So you go like, okay, that doesn't seem very, exciting. Okay, the address of the entire structure is, some 64-bit address. How do I know this is a 64-bit address? We count the number of hexadecimal digits. Okay, let's count. So how many do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. well, I'm still missing 4, okay? But the actual full address is a 16-bit address, it's a 64-bit address, which means it should have 16 hexadecimal digits. But that's okay, we just know that this is a really, really long strings of zeros and ones. Okay, so the next thing I want to do is to say, okay, but where is the first member? Okay, what do you think is the first member? I don't care about the type, I just want to know where it is. So think about what a structure is, okay? What is the purpose of a structure in CISP 360?
Basically like a class which lets you use it like a template in a way. You just describe it to an object, and that object will refer to whatever that structure lays out.
Okay, so okay, I like that word. It's a layout of something. Okay, so okay, why do we need structures? What happens if we don't have structures in a programming language? All
You have
right.
to type out the code
So
manually every single time without calling the structure to simplify it.
without a structure to package things, okay? So a structure is basically a way to package things. So for instance, think about a form, okay? Think about any form that you have to fill in. I know you have to fill in a lot of forms just to register as a student here, right? So a form, has multiple fields, okay? Because there'll be one field for your first name, a field for your middle initial, a field for your last name, a field for your birth year, a birth month, and a birth day of the month. So there'll be all of these different fields, right? So you guys know what a form is, either on paper, in PDF, or as a Google form. So what if I were to say, let's not put everything on the same sheet of paper. Instead, I give you a pile of little pieces of paper where one would ask you about your first name, one would ask you about your middle initial, one would ask you about your last name. So you end up with a small pile of tiny little pieces of paper. That is what it is like without a structure, okay? Because without a structure, you end up with all of these loose pieces of individual variables. So what is the downside of these individual variables? What do you do after you fill in your form? Well, you have to turn it into somebody, right? So what if in the process of turning in that form, that little pile of small pieces of paper, you just kind of dropped it on the floor? So now you have to pick it up, right? So how do you make sure that, oh, this one is supposed to be my birth month, and this one's supposed to be my birth date of the month, and so on? I mean, you can tell because you know your own birthday, right? But the person who is behind the counter, the clerk who's handling these forms, they do not know. All they know is, I got a bunch of little pieces of paper, and I have no idea which one is supposed to be which one. Is that okay? But on a form, okay, you drop a form on a single sheet of paper, the person goes like, I'm gonna pick it up. It's okay, because every field has its own name, and in the actual form has its own location on the form, so that the person who's supposed to process the forms can easily locate all the relevant information. Is that okay? That is the purpose of a structure. It packages things that are related into a single logical unit. Now, there are times that you want to break out these things. It's like, I just need to know the last name, okay, for sorting purposes or creating an email account or whatever, okay? It's okay. You just say, oh, of the entire form, which has a lot of information, ignore everything else, just locate the last name field. I need to know the value of the last name. So that's a member, okay? So every item in the form is a member, but the form together is basically a collection of these individual items and arranged in a way that makes sense, okay? Logically, they belong together. Is that okay? All right? Okay. So when it comes to where things are, okay, are you surprised that the very first member of a structure is at the very beginning of the entire structure itself. Because everything needs memory location, right? So the entire structure has a chunk of memory locations allocated to it. But of those locations, the very first location is also where the first member is located in the structure. Does that surprise you? Nope. Okay, it seems logical. Does it seem logical? Okay. So given that is logical, where do you think I can find M1? What is the address of M1 of ABC? And just to remind you, the ordering of these members is M1, M2, M3, M4, M5, and each one is only an 8-bit item. So where do you think I can find M2 as a member? I don't care about its value, I just need to know where to find it. We know the location of M1 ends with a 4B, so where do you think M2 is going to be?
8 bytes after that.
Not 8, because M1 is only a 1 byte thing, so it would be logical that this is the following byte, which is at location blah 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 for C. Okay, so let's double check. Okay, that kind of makes sense. So that means M3 is going to be 1 byte after that, which is location for D, and so on and so forth. Okay, so what about the size of the entire thing? So first of all, let me see if you guys remember this size of thing in C++. It is called an operator. Okay, it's not a function. But what it does is it will return the number of bytes of whatever is in the parentheses. So in this case, I have ABC as a local variable of main that we define here, like on line 9, we can still see that. So it will tell me the number of bytes that are allocated to the structure or the local variable called ABC. So how many bytes do you think is going to be, how many bytes are allocated to ABC? It has 5 members, M1, M2, M3, M4, and M5, and each member only has needs 1 byte.
That's 5 bytes.
So it will take 5 bytes, right? Okay, so let's see. Okay, it is indeed 5. So that means, okay, that seems pretty easy. Okay, so for the discussion of for the initial discussion, I want to at least introduce the concept of an alignment. So we'll go ahead and change the structure a little bit, and then we'll see, how it arranged, things to be located and how big is the whole thing. So Control D, get out of the debugger, and then we go back into the program, and this time we say, there's something else here. Okay, so uint, and this time I want a 32-bit integer, and we'll call that M6. Okay, so M6 is a 32-bit integer. Are we good? Are we doing okay so far? Okay, so now okay, I forgot the semicolon. Okay, put it here, and then we do the same thing. GCC, and then GDB. So we compile, and then we use the debugger to go into the same program, put a breakpoint on line 12, run the program again, and then we ask the very same question again. Okay, where's ABC? Okay, it changes a little bit. Okay, because the local variables are allocated on the stack, and because the structure size itself has changed, because I introduced 1 more member, the structure is now larger, so it's taking up a little bit more space on the stack, and that's why the location has changed. Okay, but that's not really even the main point of this whole discussion. So if I were to find, okay, where is the first member, which is M1 of ABC, what do you think the answer of that should be? It's still the very first member of the entire structure, so the location or the address of the first member should be the address of the entire structure. Is that okay? All right, so we are still expecting 4.4 to be the location there. Okay, yep, it is. And M2 is 1 byte right after that, so it'd be a 4.5. And then M3 is 2 bytes after that, is 4.6. And then 4.7, and then 4.8. And oops, there we go. So that's a 4.8. What about M6? Well, M6 is going to be 1 byte right after that, okay? So it is a, whoa, hold on a second here. How do we go from 4.8 to 4C?
2 bytes.
Hmm?
4 bytes.
They're off by 4 bytes. So we go like, something doesn't make sense here, right? Because why is it not 4.9? I'm pretty sure, yeah, because M5 is at location 4.8, and it takes 1 byte, so that means the following byte at location 4.9 is already available for M6. Remember M6? But why am I skipping 3 bytes to get to 4C?
Because M6 is 4 bytes because it's a 32-bit.
But that means, but it should not change the location of M6. It would change the size of the entire structure. So what is going on here? So the best way to look at this is to kind of draw a picture about this entire thing. But since I want to record everything, I'm not going to use a picture here. Instead, I'm going to use a spreadsheet. So spreadsheets are interestingly useful for a class like this. So I will put it into a place where you guys can find it. So after the class, if you want to kind of make a copy of the spreadsheet and then make some changes to it or annotate it, you can do so. And I'm just going to create it in the main folder of shared and then with the name of today's date. It is a Google Sheet. And we'll call this 2024. Today is the 14th, so that's the name of the file. So using the same convention used in this class, I'm going to use the lower portion as the low memory address and the higher portion as the high memory address. So now we say, okay, where is ABC as a whole structure? The entire structure ABC, let's say it's here. Okay, I'm just picking a spot, okay, in memory. But this is also the location of M1 as a member. The next location is where I can find M2. And then the next location is where I can find M3. I mean, this part is kind of boring. abc.m4, and then we have abc.m5. Okay. So in terms of the actual location, we have 4.4, 4.5, 4.6, 4.7, and this is 4.8. Okay. So are we understanding what this picture is about? Okay, it is just a more pictorial version of what we saw in the debugger. And I only kept the last or the least significant 2 digits of the address because the rest really does not matter to us, okay, because we are just looking at the relative positions of the members, okay? So we go like, okay, so the next one is, this is 4.9, which is not used, for A, 4B, and this is 4C, okay? This is location 4C. And this is where we find abc.m6, and M6 itself takes up 4 bytes. So these 4 bytes are basically collectively used by M6, and I'm just going to use some color coding here to kind of highlight it so that we know that, oh, okay, these are all kind of the same thing, okay? So these are all the same thing, and each one of these is different. The question is, why am I skipping 3 bytes? Well, that has to do with the word size, the natural word size of the processor. So what do you mean by the natural word size of a processor? So inside the processor, okay, let me kind of pull up the diagram because I think it's good to be able to see a diagram to understand what I'm talking about here. So I'm just going to start up Logisim and bring up my own processor architecture. Okay, so we'll open this one here. Okay. So the natural word size of a processor has to do with what is the width of the data bus. Okay. Now in my processor, because it's a very simple processor, the data bus, the wire, the number of bits for the data port here is only 8 bits, which is 1 byte. Okay. So that means every memory cycle can only either read 1 byte or it can change 1 byte at a time. Okay? What do you think a modern architecture should be able to do? How many bytes per read and how many bytes per write? A lot more, okay? A lot more. And what is the instructions? What is the name of the instruction set used by most PCs, not counting Macs these days? It's called AMD 64. Okay, so the computer architecture that we use on most computers today are 64-bit architectures. But what does it mean? Why do we call these 64-bit architecture? Because the interface to memory is 64-bit wide or 8-byte wide, which means it can read 8 bytes at a time. It can write 8 bytes at a time. Is that okay? But it can only do that when we are what we call byte aligned. In other words, the way the memory is organized. So let me kind of close this one or minimize for a while. So I'm going to use another sheet to illustrate what I mean by byte alignment. Okay, so let's just say that this is location 0. Okay, so location 0 is and the following 7 bytes is basically, I'm trying to figure out the best way to describe this. Okay, we'll see whether this works. If it doesn't work, let me know. So I'm going to highlight 8 bytes here. 1, 2, 3, 4, 5, 6, 7, 8. So that's 8 bytes, and I'm going to color code it using a particular color. Okay. So these basically in a single memory read, I can read or write these 8 bytes. I can choose not to change all of them. I can choose to change only one of them, but I can also choose to change all of them at the same time. Is that okay? So the next chunk of 8 bytes that I can read or write is going to be right here. 1, 2, 3, 4, 5, 6, 7, 8. So these 8 I can also change at the same time, or I can alter at the same time. I'm going to choose an entirely different color here. Is that okay? So the entire memory space is basically divided into chunks of 8 bytes, where each chunk can be read or written to in one single memory cycle. Is that okay? So you go like, well, what does that have anything to do with what we are talking about here? So now we look at, so now we try to superimpose what we have here onto that one, okay? So I am going to copy like this portion. Okay, so let me select this portion, Control C, and then you paste it. Now I have to be careful where I paste it because I think I should paste it here. There we go. Okay. You go like, okay, so what, right? So the question is, what if I try to save memory space and I put abc.m6 right here? Okay.
It's not gonna fit.
It's not going to fit. Okay. So that's a very good observation. It's not going to fit. So let's I will duplicate this sheet here so that we can now see what happens if it doesn't fit. Okay. So that means I'm hypothetically saying that let's move this into here. So Control X, Control V, and then this is still location 4C, but now this is location 49. And now these 3 bytes are not used. Okay, so we'll clear the formatting, and instead these 3 will be used instead. Okay. Is that okay so far? So if I did not waste the 3 bytes in between and having M6 immediately following M5, then you go like, okay, so the 32-bit integer that is M6 is now taking the last 3 bytes of the first 8-byte chunk and is taking up the 1 extra byte of the next chunk. So the question is, can the processor still kind of read and write M6 as the last member? The answer is yes. Okay, it is completely transparent to software that the processor can still do it. It's not a problem. But the downside is it now takes 2 memory cycles to get it. The first memory cycle will get the first 3 bytes out of 4 of M6, and it needs 1 additional memory cycle to get to the extra byte that now belongs to the next 8-byte chunk. Okay? Well, can it be done? Yes. Can it be done efficiently? The answer is no. That is the reason why we need alignment. Okay? So that means, if I want to make sure that I can read M6 and write to M6 in 1 single memory cycle, then I need to use this particular way. Because this way, even though I am wasting 3 bytes here, okay, this byte, and this byte, they're all wasted. They're used for nothing. But I make sure that if I need to read or write M6, I can do that in 1 single memory cycle. Is that okay? Yep.
Just to make sure I understand. So the next M6 takes 4 bytes, right? Or
Yep.
4 bytes.
4 bytes. Each cell is 1 byte.
And that's only 6 over 4 rows. But why does it jump from 48 to C instead of 49?
Because 49 is here, for A, for B, those are the 3 bytes here.
So
They're not used for anything. I mean, you can write those here, okay? It's not a problem to write these here, but they are not used in this particular structure.
what's A, B, and C? Should it be like 50, 51, 52?
These are just relative. This is saying if the beginning of the entire structure is at 44, then the address of M6 as a member will be at location 4C. So we're only looking at the relative distance.
No. For C, why not 50, 51, 52?
Space 16 decimals.
Because they are in hexadecimal.
Okay.
Yep. Oh, thank you. I missed the question entirely. Question? Yeah.
So could we use those like empty bits?
Empty locations?
Yeah, empty locations for anything else.
You
like-
cannot use it for anything else.
So they're just.
Because we're looking at one structure, right? So the whole thing, so when we look at the structure, how big is the structure? The structure is now from here down to here. So if I were to put like a box around the whole thing, this is why I like spreadsheets. This entire box is variable ABC.
Could
So
you
now, yep,
put
go ahead.
3 more 1-bit in those 3
Oh, yeah.
locations?
Yep. So that means, if I have a M7, that is declared right after the M5, it'll be stuck here. But the ordering is also important. So unless you say something about, I need everything to be as compact as possible. If you specify that to the compiler, that you want to compactify and use the least amount of space, then it will try to pack M7 here regardless of the actual order of M7. But compilers usually don't do that, so it would try to put M7 over here if M7 is declared right after M6. Yep.
So let's just say M6 is a 1-bit, or not 1-bit, 8-bit, and then M5 is actually the 32-bit, and would that 4-bit be right after M4, and then M5? Then the next bit would be on the next bit over.
Can you say that one more time?
So let's just say M6 is 8 bytes, right?
Okay.
And then M5, let's just say M6 and M5 swap places.
Okay, that's a
So
very
will
good
it
question.
will it go for M4 and then the next 4 will be M5, or will the M5 be on the
Okay.
next byte over?
So if they were to switch order, then M5 would not be here anymore. Then I have actually 4 bytes available, and then M6 will fit here perfectly, and then M5 would be here.
Okay.
Okay? So that's a very interesting observation. Let's do that because there's one side effect that you may not expect when we do something like that. Okay, because you're basically saying, oh, I can reorder things so that everything fits, and I can still use only one memory access per item. Okay, I think that's what you're shooting for. Is I don't want to waste any space, right? Okay, so let's check out what happens in that case. But before we do that, we also have one more thing to do, which is to check out what is the size of ABC in this case. Okay, so I'm not sure which window I was using before. Yep, right here. Okay, so now we say, okay, tell me what is the size of ABC. What do you think it should be, according to the picture that we saw earlier? So let me go back to the picture. So what is the size of, which is in number of bytes, of the entire ABC?
16.
No, 12. Okay, it should be 12 because it goes from here to here. Okay, so this box is representing the entire structure. So 12 is, this is what we kind of expect. And it really is the answer as well. Okay, it is 12. Okay, so it's all good. Do we have any questions at this point? Nope. Yep.
My other question is, how do you know where something like a structure is going to start? Is it guaranteed to start in the beginning of one of those details? Or
Yes. Okay, so there are a few factors. Okay, so we'll get to that. Where it starts is also has to do with alignment, but it doesn't have to be 8-byte aligned. It just has to be aligned to guarantee that each scalar type contained within the structure can be accessed in one single memory cycle. That's all it needs to guarantee. Okay, so we'll keep that thought in mind, and then we'll switch to it. We'll change the code a little bit so that we address what you were asking earlier. Can we optimize the ordering of the members so that we end up saving? We don't lose those 3 extra bytes, right? So we'll do that. Okay, so we go here and we'll do the editing exactly as you suggested. So we'll have M1 to M4 together, M6 by itself, and then have M5 to be here. Is that what you were suggesting?
Kinda, but I was kind of, when in 5 was the 32-bit and in 6 was 8-bit, will it be on one byte?
It will still be the same thing, right?
Yeah. Yeah, pretty much, yeah.
Okay, so we're basically just making sure that the number of the member is correlated to the order. Okay, which is fine. Either way, it's fine. Okay, so we'll go ahead. Okay, compile the code, and then go into GDB. Put a breakpoint on line 13. Okay, so we'll still ask basically the same question. Same location as before. Not surprising. abc.m1, also at the very beginning of the entire structure. So far so good. Okay, everything is as expected. Okay, so we'll go like, okay, let's check out M2, M3, M4. Okay, no surprises here. M5 is all good too. Okay, because we don't need to waste those 3 extra bytes because it is now the last 4 of the 8 bytes that we can use in one single memory cycle. And then M6 is going to be, whoa, what is going on here? Why is M6 all the way over there now? Because the compiler is still trying to make sure that things are aligned. And in this case, it doesn't really do such a great job, does it? So now, okay, so what do you think is the size of ABC now?
12.
I don't think it's, it is still 12. You're correct. It is still 12. It's just wasting, 3 different bytes.
So it's still wasting 3 bytes either way.
Yep, it is still wasting 3 bytes, and those 3 bytes are the ones
Yeah, it's between.
between M5 and M6. And I did not expect this. This is not what I expected. This is like, oh, okay, that's kind of interesting. Did I recompile the code? I did recompile the code. Yeah, so M6 is the 1 byte thing. M5 is the 4 byte thing.
Maybe recompile again.
No, this is actually correct. Okay, I see what is happening. Okay. All right, so what is happening here is 4C is correct, okay? Because after we made all the modifications, the new map, okay, so the new map is almost the same as what we have here with a very minor difference, right? Okay, so there's one thing that is explained and one thing that is totally not explained. So now we have M5 taking 4 bytes because that's our 32-bit integer. M6 should only take 1 byte. So these 4 should not be highlighted at all. So we'll go to format and clear the formatting. M6 only needs this location, right? So that means the entire structure should only take 9 bytes. But it is now saying, let's waste these 3 bytes too. Okay, so let me just kind of, okay, the memory locations are still here, right? So that's consistent with what we saw in GDB, because in GDB, when I asked where's M6, it is now at 4C. When I asked where's M5, it is at 4.8. So that part is still consistent. But instead of saying the entire structure should end here, it is still saying, let's waste these 3 bytes and end the structure at location C, this is D, E, and F, and the entire structure at 4F. Why is that? Yeah.
My question was, you said it's supposed to be 9 bytes, but we
Yep.
know it's 12 because of the M6, right?
M6 is only 1 byte wide now. So that means if the size of the structure is only including the bytes that are occupied by the members, that's the size of it. Okay, this is supposed to be the size of the whole structure. So the question is, why do you think the compiler is still saying, no, it has to be this big? In other words, we are still wasting 3 bytes. But this time, the 3 bytes that we are wasting are these 3 bytes.
That's because of M6, right? 'Cause
No, M6 is only 1 byte now. We changed the type of M5 and M6. M5 is the one that is 32-bit. M6 is the one that only has 8-bit. So that means this is the portion of the memory that is actually occupied by the members of the structure, which also asks, so the question is asking, why are we still wasting these 3 bytes here? And I have the answer. I have the perfect answer to this question.
the memory allocation.
But why? Why are we doing this? Why are we wasting 3 bytes? Yes?
Is it because it's actually not like the 8 byte chunks that you have in the A column? Is it not actually aligned there? I would expect it to end at an F, right? You would think it would end at.
It should end here, right?
What should it end at?
It did not.
But why wouldn't it end at 4F?
It would not end at 4 what?
F?
4F? So it does end at 4F now. So this is for the, for E, this is 4F.
Yeah,
So
but in column A, where you have the 2 different 8 byte chunks.
Yep.
Why wouldn't the 8 byte chunks end at something like 4F and then restart at 5.0?
Oh, this is offset already. This part here is actually already offset a little bit. Okay, so that part is already off because if you look at divisible by 8, these are the 8 that belong together, and then these are the 8 that belong together. These 8 here belong together. Okay, so let me just use a separate color highlighting here. So these 8 is belong in one chunk, and then these 8 is actually in a different chunk. In other words, the structure itself is crossing between the 2 chunks here. But it's not a problem because remember what the objective was. The objective was for any member that is a scalar, okay? I want to make sure that I only need one memory cycle for each scalar type. Is that okay? So what scalar types are we talking about? What member are we talking about? M1 is just 1 byte. So in order to read this 1 byte, if I read all the green bytes, is that a waste? It's not a waste, okay? I need to read at least one memory cycle to get to that 1 byte, so it's not a waste. M2 is also just a 1 byte thing. Is it a waste if I have to use one memory cycle to get to it? Not a problem, not a problem, not a problem. So when we get to M5, it's a 4 byte thing, but we are reading 8 byte at a time. So that means regardless of where M5 is within these 8 bytes, I'm gonna have to need one memory cycle to read M5. Is that right? Okay. So, but it still doesn't, so M6 is also not a problem because it's just 1 byte. If I need to read all the pink bytes just to get to M6, well, that's what I have to do because every read operation is gonna read 64 bits. I don't have a choice to read only 8 bit. I have to read all 64 bits and say, you know what? Of the 64 bits, I'm gonna toss away the other 56 bits because I really only care about these 8 bytes, these 8 bits or this single byte. Okay, but the question is, why are we still wasting these 3 bytes here? It doesn't seem to make sense. It makes sense when you're trying to use the entire structure X in something else. Okay, so what do you mean by in something else? So in this particular picture, I really should erase this portion here because this portion really does not matter. I mean, it's actually incorrect, based on the location of these bytes. Okay, so now going back to this code here. Okay, we are going to change the program a little bit, and this time I will use struct X in a struct Y. So struct Y is going to consist of 2 members. We'll call it A and B, and they're both struct X's. That is why a struct X needs 12 bytes. Okay, so we'll take a look at what happens here. So now we have struct Y being ABC, and we want to change the A.M1 to be a 0. Okay, so do we have any questions about the source code in C at this point? We have struct Y having 2 members. Member A and member B of struct Y, they are both of the type of struct X.
Which means they each have 6 members.
Huh?
Which means they each have 6 members, right?
Each one has 6 members. So that's why when I want to designate a scalar type for initialization, I now have to say ABC, which is the name of the variable, dot A, which is one of the members of a struct Y, which by itself is a struct X. And then of the struct X, I want to access M1, which is this thing here. So let's take a look at how the memory is going to be allocated in this case. Okay. So the way this is going to be allocated, I don't even use a compiler yet. Okay. So the way I do this is I'm going to copy these over to another sheet. And then this time I have 2 of those. Okay, so one is here and the other one is here. Okay. I can let me see if I can. I'm just reducing the size so we can see the entire thing. So that means from the perspective of ABC, which is now different, okay, these are all incorrect at this point. So I'm gonna have to erase all the names because they're all a little bit different now. Okay. So if you look at ABC as a single variable, it's now taking up 24 bytes. This entire portion, okay, I can merge cells and give it a color, okay. So now this entire portion refers to variable ABC. Is that okay? What about just this portion here? The first half is referring to ABC dot A. Okay, we'll also do the same thing. Merge the cells and then give it also a slightly different color. We'll just pick green this time. What about this portion here? What is that corresponding to? Dot B, that's right. Okay, so this is all ABC dot B, and we'll give it a different color. We'll give it a blue-ish kind of color here. So now I can now name the individual ones. This is now ABC dot B dot M1, and this is ABC dot A dot M6. But do you see why we need those 3 extra bytes? Those 3 extra bytes, make sure that if I use the type struct X as one single type within something else, that it will always make sure that things are aligned correctly, so that I don't need 2 memory accesses to access a scalar type. Is that okay? All right. So yes, it is a little bit on the wasteful side in terms of the utilization of memory, but it does improve performance significantly, because otherwise I need 2 memory accesses instead of 1. Yes.
So if we added more 8-bit variables, so
Mhm.
we added 3 more, would that fill up the blank space?
Yep.
Without adding
Yep.
any gaps?
I like that question.
The
Yep.
4th variable, would it now have the 3 gap, or would it be more?
Haha. Okay, that's a good question. So let's do the first one first, and then we'll answer the second question second. Okay. So right now, at the end of the entire structure, we got 3 extra bytes that are not used for anything, right? So that means, if I were the compiler, and I can even say, okay, let's use 2 bytes for M7. This is M7, and I have 1 byte left, which is now an 8-bit thing for M8. So they should all fit within the 12 bytes, okay? So we'll run that experiment. But I need to kind of pause right here, is to kind of recognize the way of thinking. Because what you're thinking is, okay, if my understanding is correct, this something that you have not talked about yet, this is what I expect you to do. Now, this is a very important way of learning, because you are basically absorbing the material. You have a certain theory of how things should be done, and then you're applying it right away to a hypothetical case that we have not talked about. Now, there are only 2 possible outcomes. You're either right or wrong, okay? But in either case, you're learning something. If this turns out to be exactly what we expect it to do, congratulations, okay? We have a confirmation of your understanding. That's great. But what if the outcome of the experiment is not what you expect it to be? Well, it's even better, because it is pointing out that your understanding, or my understanding, because after all, I was teaching this stuff, right? So that means my understanding is not exactly correct, okay? And that is an opportunity to go like, okay, what am I not understanding correctly? And that, to me, is actually one of the most important part of learning, is to design experiments, okay, that is not just a regurgitation or a repetition of what I do in class. Have an expected outcome, and then double check the expected outcome is indeed the outcome. Okay, so that's a very important technique of learning. So when I say studying, this is actually the activity of studying, is to say, okay, I understand the material, or at least I think I understand the material, but if I understand it correctly, then this hypothetical case should have this outcome, and then give it a try. Okay, so we'll exactly do that. Okay, save the code, and then GCC, GDB, put a breakpoint on line 19, run the program. Okay, so now the first thing, the one thing that can tell me whether my theory is correct is to look at ABC, okay? Or just to look at one of the members of ABC. We can look at just A, or we can also look at struct X. So all of these are ways to get to the same information, which is it still 12? Because we have those extra 3 bytes that were not used before. With those 3 bytes, I'm now adding a 16-bit thing, which is a 2-byte thing, and adding one more 8-bit thing, which is a 1 byte thing. It should all fit within that extra space that we have. Is that okay? So it is now a 16. So my theory is wrong. It doesn't pack everything. So now the question is, well, if it doesn't pack everything the way that we thought it should, then where is the 2 extra variables? Okay, so that's where we are gonna find out. Okay, so we'll go check out where is ABC dot, I think M6 was the last one that we had before. Okay, oops, ABC.A.M6. There we go. So that's the last one that we had. And now we check out with M7. So the 3-byte gap is right there. Because M6 should have taken up only 1 byte. So M7 should be right after, which is at location 39, but it's skipping 2 bytes to get to it. So that means it doesn't like it when a 2-byte thing is at an odd number. It wants to make sure it is at an even number. So the start address of a particular scalar type has to be divisible. If you look at the address, it has to be divisible by the size of the scalar type. Let me say that one more time, okay? The start address of a scalar type has to be, as an address, it has to be divisible by the width or the size of the scalar type. Because in this case, if this were 39, it is not going to be divisible by 2. And 3A is. Okay? So now we say, okay, so let's say that is the case. So that means if I change the ordering of M7 and M8, then it should all fit. Because now it will force M7 to be at an even address, and everything should fit, and I should only have 12 bytes. All 12 bytes will be used in this case. There'll be nothing wasted. So we'll do this again. GDB. Oh, I just my palm touched the keyboard. There we go. Run the code. Print struct x. Print size of struct x. Now it's back to 12. So that is the theory. So basically, I had a theory. I observed the outcome. It's not consistent. We're not packing things as tightly as possible. So what is the theory? The theory is the beginning address of anything that's more than 1 byte, which can be 2, 4, or 8, has to be divisible by the size of that thing. All right. So now you guys go like, oh man, all this stuff is kind of complicated. So we have to learn how to allocate memory for all of this stuff here. Well, as it turns out, none of that really matters, because Textoy processor is a 1 byte aligned kind of processor. So there's no need for consideration of alignment. Yes.
Can you repeat what you said with the size of the, what was it, the address?
Yes. So let me go back to, it's right here. So I'll just write it here, okay? The start address of a scalar type has to be divisible by the size of the type. That's basically what the compiler is trying to make sure. Which is kind of odd, because even if we were to get to, well, okay, it's odd and not odd, because because of the long history of how the x86 architecture evolved into the current point. So I can kind of see why they want it to be like this, because the AMD 64 processor, or the instruction set, has Okay, this stuff you don't have to remember this. I'm just gonna tell you this, but you don't have to remember. There are registers A, B, C, and D. Okay, in the architecture. Okay, but they're not because of the letter. Okay, but they don't. A, B, C, D corresponds to accumulator, base, counter, and I cannot remember what D was. Okay, but each one has a special purpose. When the architecture was an 8-bit architecture, register A is really just an 8-bit register like the one that we have. When they came up with the 286 processor, the registers become 2 byte wide. I think 86 is already 2 byte wide. So register A now got a new name. It's called AX for A extended. Okay, and when we switch to 32-bit architecture, register A becomes EAX, which is, I cannot remember what E stands for, but now that we have a 64-bit architecture, it also has a different name. So because of that, okay, when we try to access a 2-byte item, it still wants the 2-byte item to be at an address that is divisible by 2 itself. So that's kind of the deal with the Intel architecture. That's kind of unique to the Intel architecture. But you don't have to worry about that, okay? Because the text toy processor does not have any alignment issue. Is that okay? All right. So from here on, okay, when we write code, we'll be looking at from the perspective of your text toy processor. So let me go ahead and write 2 programs, and we'll just okay. Okay, I'm gonna erase some of this. Okay, we'll change this back to as simple as we can. And uint8_, we'll introduce M0 so that what we need to get to is actually one after that. Okay, so let's say we have 3 members, M0, M1, M2 in the C code, and I want to convert this into the assembly code. Okay, how do we do this? Okay, now one thing I haven't really mentioned because I haven't really thought about it that way is the conversion process really has more to do with what is going on, what is expected to be going on inside the processor than the actual language used to express it. So the first thing we need to do is to look at the C code and ask, what does it mean to have a structure that has M0, M1, M2 as members, and specifically for text toy processor, where there's no issue of alignment. Okay? So you can always draw a picture. Okay, you can always just kind of draw a picture here, and just say, if we have a structure of X, then M0 is going to be the first byte. Okay, this is the address of the entire structure, and then M1 is going to be 1 byte after that, and then M2 is going to be 1 byte after that. Is that okay? That's kind of just following the order of the members. Is that okay? But there's no structure definition in assembly code. Okay, so you cannot say struct blah 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 in assembly code. So what I do instead is I basically use labels. X_M0 is defined to be 0. The reason why that is the case is this is the offset to find member M0 from the start of a struct X. In other words, I'm only keeping track of the offsets. Okay, if I know where a struct X is, this is the number of bytes from the beginning of an entire struct X to the member M0. Is that okay? Does everybody understand the purpose of this label? Okay, so the next label is going to be, if I know where the entire structure is, where do I find M1? Well, you can put a 1 here, but the way I do it is I do it this way, because I want it to be at an offset from the previous member, because this way if I need to add or delete members in the structure, it is easier. I don't have to recompute all the numbers. Okay, and then M2 is over here. And it is 1 byte after M1 because M1 itself is only taking 1 byte. Then I need one extra label for the size of the entire struct X. So that's going to be the offset to the last member plus the size of the last member. So this is the size of a struct X. Is that okay? So lines 3 to 7 in the C code on the left-hand side essentially translates to lines 5 to 8 in assembly code. This is how I can keep track of a structure and know where to find what. Okay. Yes?
Is the line 13 on the C code supposed to be NZ?
Line 13 on the C code. What about it?
Is the ABC dot NZ?
I want it to be M1. I want to initialize the second member. Yep. It's okay. Okay, so I may run up. Yeah, go ahead.
So the x underscore of 0, 1 plus is just incrementing.
It's a postscript notation, which means we are basically, the plus asks what are the two items that we already have seen. We have seen M1, we have seen 1, add them together. So that's a postfix notation. We specify the operation after we provide the values.
Why not just do x underscore M1 semicolon 1 like you did with 0? With line 5, why not do the same thing with 6, 7?
So, okay, can you suggest again what we want?
Like you see how you have x underscore M of 0 and 1 plus, because you're specifying that you're adding those two terms, right?
Right.
Why not just do 1? Why are you adding?
Because this way, if I want to add additional members before M0, I don't have to change it. Because everything is relative to the one before that. So that makes it easy for me to add additional members either before or after.
Okay.
So I'm setting it up so that I can modify the structure without having to recompute all the values by hand.
But you can still do that though, right? You can just
Yes, you
do
can.
1 and 2.
Yep.
Okay.
But
Just wanted to
I
make sure.
choose to use the most flexible way for the future, in case I need to change the structure.
Okay.
Yep.
Are we putting in the structs in the stack?
Hmm?
Are we putting in the structs in the stack?
Yes, we are, but we haven't gotten to that point yet. Okay. Okay, so I have to answer one potential question that some of you may have. It's like, but why are we spending so much time to talk about how a C thing is done in assembly code? What is the importance of that? Well, the first importance is some of you may end up writing or maintaining compilers. So this is all super important if you want to write compilers. Okay? And some of you may end up writing code that has to interface. You have to write code in assembly that interfaces with regular C code. In other words, you have a program, part of it is written in C, and the other part is written in assembly. That is when you really need to know, oh, the C code is calling me with the address of a structure, and I'm supposed to do blah, blah, blah with that structure. How do I get to the member of the structure pointed to by the pointer? Where do I even find the parameter on the stack? So that is when that becomes useful, is when you need to write code where part of the program is written in C or C++, and the other part is written in assembly. And you might ask, who would do crazy stuff like that? Well, I wrote a little real-time kernel entirely in assembly. And the interface or the API to the kernel is from C and C++. So the regular GCC compiled program can make use of the real-time kernel, which is a tiny little operating system that I wrote, so you don't need to write the entire thing in assembly. You can still, the client, my clients, can still write code in C and C++, even though my code is written entirely in assembly for efficiency and other things. So that's why. Anyway, getting back to this. All right, so now what do we do about this code? Okay, so we have no op at the very beginning of the whole thing, LDI D0, initialize the stack pointer, and then we call main. Okay, so main is now considered to be just a regular function, so we call it. So now we go like, okay, let's call main. And to do that, we have LDI A with the return address. So we'll just say, there's only one single return address here. We'll just use a label for that. Decrement D, STD A, that will push the return address. And then we have a JMP I to main. And when that comes back, we have a halt. And then this is also where return address as a label should be defined, because that's, oh, okay, I take it back. This is where it's supposed to be, because it's supposed to be right after the JMPI instruction. So now we have to write main. So from the perspective of main, what is ABC? ABC is a local variable. And where do we put local variables? Okay, so now you have to remember what we talked about in the previous 2 lectures or so. Parameters and local variables are all part of the frame, and the frame is on the stack. Exactly. Okay. So that means the entire ABC is supposed to be on the stack. Okay, now do you remember how we used the labels to kind of keep track of what is where on the stack and how many bytes we need for local variables? Okay, let me see if you can remember this. Okay, main ABC, it is the only local variable, so by the time we're done with all the allocation, it'll be exactly at where the stack pointer points to. Okay, because we only have one single local variable here. But then, oh, okay, I just got a typo here. But then we also have to keep track of LVS, okay? LVS stands for local variable size. How many bytes do I need to allocate for all the local variables of main?
1.
Nope. Nope. You- Exactly, it's the size of a struct X, okay? So that means this is going to be the offset to the last local variable. Okay, since I got only one local variable, it has to be ABC. But then we have to add the size of a struct X. That is the number of bytes that I need in order for all my local variables. Is that okay? So this part is actually consistent with what we have already talked about in the previous 2 lectures, okay? Because where do we put the local variables? On the stack, okay? And how do we calculate the number of bytes that we need for all the local variables? It is still the same method. The only change right now is ABC as a local variable is not just 1 byte. The size of ABC is represented by the label X underscore size. And that's why I have to keep track of all these things. Okay, what about the rest of the program? We have to allocate the space because remember, a callee is responsible to allocate the space for its own local variable and to deallocate that too. So now we need LDIA with main underscore LVS. Subtract that much from the stack pointer to allocate. Okay, this is for allocation of local variable. And then we have a bunch of stuff to do here, which I'm gonna deal with that later. But then when we exit the code, we have to remember to deallocate all my local variables. So I'm adding this number back to the stack pointer to deallocate. Then we can do the usual return, which is LDBD, increment D, JMPB. There we go. So that's the usual code that we use for returning. So now in between, we have to ask the question, how do we do the assignment of a 0 to M1 of ABC? Okay, we are running out of time fairly quickly, but I'll finish this code and then you guys kind of quickly. So first thing is we have to get to the structure of the address of ABC. So that approach has not changed. So we do LDIA with main underscore ABC because that's the offset to local variable ABC from where the stack pointer points to. Add AD, that becomes the address. Okay, so I'll comment. So this A is the address of ABC minus the stack pointer. By adding the stack pointer back to register A, this now is the address of ABC. Oh, if we already know where ABC is and we know relative to the address of ABC where member M1 is located, we can just add those two. So now we do LDIB with X underscore M1 because we're trying to get to M1. So this is basically offset to member M1. And when we add A and B, A is now the address of abc.m1. And we want to store a 0 to that location. So the 0 has to come from somewhere. And register B is now free. So I put a 0 into B. STAB is going to store, it's going to complete the operation. So abc.m1 is getting a 0 with this instruction. So that finishes the whole program. I don't have enough time to explain this one, so I'll do the explanation in the next class, okay, next Tuesday. But you probably want to read this code. You can run it and look at the outcome of this, in the trace table, and be able to go like, okay, if I were to, figure out which byte is used for what, am I seeing what needs to happen in this case? But I'll come back and explain this one on next Tuesday. All right, so I'm gonna stop this, okay, and go back to the class because we have a lab and a homework assignment. This is the first time you guys actually got a homework assignment that you have to spend time to do, after today's class and before I give you guys a whole week to do this. So the first part is really just a lab in the sense that it's in the same format as all the other labs, okay? You have multiple choice questions, and there are some you have to calculate the numbers and whatnot, okay? So that part is due to do today. The second part is a program that you have to finish. The lab itself will tell you what program you have to do, okay? So by doing the lab portion, you will know what the program is supposed to do, and then I give you 1 week of time to finish the actual program. Is that okay? So it's a little bit different setup, compared to the past labs, because this one actually has a component that you will have to spend extra time to complete, over like 7 days of time span. Right. So I want to open this in a new tab because I need to show you the access code. And there's none. Is there access code?
No.
There's none. Okay, so you guys can all get in right now. So that part is still due today at noontime. Yep.
Can I see that the ASM button?
Sure. I can actually send that to the whole class.
Scroll down.
Oh, that's the just the normal kind of return code.
Okay.
Mhm. And I'm gonna try it out too. So we'll. The lab today does not have anything to do with structure, by the way. So that's why it's okay for me to defer some of the discussion to next Tuesday. All right, so I hate to disturb your lab, but I just ran the program and it is consistent with what I expected to do. So that means over the weekend, if you have time to kind of review this sample program, you can kind of use this trace to help you kind of get an idea of how the whole thing works. And I'll send the code to you guys too, by announcement.